Good afternoon, everyone. My name is Jeffrey Zhang. Today, we are going to talk about multicast in segment routing networks. With segment routing being deployed or considered by more and more operators, those with a multicast requirement may want to consider what options they have to do multicast in a segment routing network. And so who may have a multicast requirement? Multicast is for distributing information from a single source to multiple receivers. It has been used for a long time for many use cases, including IPTV, video distribution, financial data distribution, and some enterprise may use it internally for multi-point delivery. Multicast will also become more important with more and more real-time, large-scale distribution of high data rate content. A classic example is the World Cup soccer games, things like that. So today we're going to talk about segment routing principles and corresponding multicast options. We will talk about controller signaled P2P tunnels. We'll talk about BGP signal multicast, end-to-end inter-region multicast, and finally, if we have time, we'll talk about multicast with transport, with classful transport. A quick background on multicast technologies. First, we have IP multicast. An IP multicast flow is identified by a source group address pair. It's forwarded along a tree that is typically set up by PIN protocol, and that tree is specifically for that source group flow. And then we have multicast tunnels. A single tunnel can be used to transport many multicast flows through part of a network. The tunnel could be an IP multicast tree itself. It could be a RCDP TE P2P tunnel or MLDP P2P tunnel. It could be ingress replication or the latest beer tunnel, which we'll talk about briefly. And then there is MVPN, basically multicasting a VPN. How do you transport customer multicast traffic over a provider network? There's Rosen MVPN and BGP MVPN. It involves PE2P signaling of customer multicast state, basically which PE needs to receive multicast traffic, and also PE2P forwarding of the customer multicast traffic via the tunnels. So principles of segment routing. The way I see it, there are two. The number one principle is that we no longer have per flow or per tunnel state inside the network anymore. The packets themselves have embedded segment lists for traffic steering across the network. The second principle is optional but preferred use of controllers. The controllers are used to instruct ingress node to embed that segment list in packets so that it can be used for traffic steering. Now, when you look at the SR principle number one, no per tree state inside network. To do that, there are two ways. One is the ingress replication. Basically, the ingress router will send individual copies to egress routers, and the transit routers have no idea that it is multicast traffic. The second one is beer. With beer, the packets will carry a bit string. Each bit in that bit string indicates a particular edge router that needs to receive traffic. And the transit routers will look at that bit string and figure out which next router the traffic should be forwarded to. If the beer gives efficient replication across network, just like the traditional pin multicast tree or MLDP tunnel, but unlike those, beer does not require per tree state inside the network anymore. Technology-wise, beer is the best technology. It's relatively new, um, but it requires a new forwarding plane, so its deployment has not been ideal. So in today's presentation, we'll actually not cover beer, or talk about cover other multicast topics. I want to point out that both ingress replication and beer, they stick to the SR principles. However, they are actually independent of SR. They even without SR, they can still work. The next principle is the use of controllers. When it comes to multicast, there are two ways to do that. Um, the first one is that the controller calculates a P2P tree, and then the result of that calculation is sent to the tunnel ingress, and the tunnel ingress will then use the existing RSVP TE P2P tunnel to set up that tunnel. That we actually have an implementation and actually deployed in production network in a European tier one provider. The next one is that not only the tree is calculated by the controller, it's actually signaled by from the controller directly to the tree nodes as well. This include the SRP2MP, or also known as tree SID. It can also be MLDB tunnel that is signaled by the BGP from the controller. I want to point out that all these RCPT P2MP tunnel or MLDB tunnel or SRP2MP tunnel, they have identical forwarding plane. You still have per tunnel state inside the network. You have incoming label for a particular tree with the corresponding replication branches. So in the forwarding plane, nothing has changed. So it does not stick to principle number one of segment routing. It does use controllers here. So looking at all those options, this could be considered in the order for multicast in segment routing network. If you care about efficient replication and you do not want to have per tree state inside network, and most of your replication points can do beer, then beer is the best technology, period. However, it could be that in an existing network, your existing router just cannot support beer at all because of the new forwarding plane. In that case, the traditional multicast, whether it's PIM or P2P tunnel or even ingress replication, can still work well as long as you don't need a controller, or and you don't mind running those in the XR network for multicast purpose. There are some operators who say that I am using SR, I no longer use LDP or RCDP for unicast anymore. Therefore, I want to get rid of those protocols from my network entirely. I don't want to use it for multicast either. Some will insist that. Some other operators could be practical, saying that I don't use RCDP or LDP for unicast anymore, but I can still use MLDP or RCDP for multicast only. That's totally fine for some operators. And then if you really need a controller to calculate trees so that the trees calculated is according to some calculation constraints, for example, bandwidth and protection, all those things. If you care about that, or if you really want to remove the legacy multicast protocols, then you can consider controller signal in multicast. I just want to point out that with controller signal multicast, we will still have per tree, per tunnel state inside the network. In other words, it does not to stick to the segment routing principle number one. And in this session, we are going to focus on controller signals P2P tunnel. The first option of controller signal P2P tunnel is SRP2MP, or previously known as tree seed. It's being worked on in several IETF working groups, each focusing on different aspects of that SRP2MP or tree seed. Basically, after controller calculates the tree, it will signal replication segments to each tree node. Here, a replication segment is the forwarding state for a particular tree on a particular node. So that it includes the forwarding state identification, which includes root ID, tree ID, candidate path, and target nodes, which nodes on the tree this is about. And also include forwarding information like incoming label, outgoing branches and labels, things like that. The signaling for SRP2MP from the controller can be by PSAP or BGP Multicast or BGP SRTE. And in this presentation, we're going to focus on BGP Multicast. The next one is MLDP tunnels signaled by BGP from controllers. Here, it's basic label forwarding, just like SRP2MP or legacy MLDP. However, the only relevance to MLDP here is that MLDP flag is used as the tree identification in the control plane. We actually do not use the LDP signaling at all. We just use the MLDP flag to identify a tree in the control plane. The reason for that is that MLDP flag has a flexible and extensible opaque structure that can be used for many situations, very versatile. And it also allows easy transition from existing MLDP deployments. For example, you may have a BGP MVPN with MLDP provider tunnels, spans a large network, and you may want to change part of that MLDP tunnel to be set up using BGP from controllers, just in the core network. But end-to-end tunnel is still MLDP. So MLDP tunnel signaled from BGP via BGP can be done from either from the controllers, or it still be the hop like the traditional MLDP is done hop by hop from leaves towards the roots, except that instead of MLDP label mapping, now we're using BGP message. So next, we're going to focus on BGP multicast. BGP multicast is basically that you're using this new CFI called MCAST tree CFI to signal for SRP2MP, to signal for MLDP tunnel and IP multicast, or any potential future tree types. We just use a different ROI type to identify the tree. It can be signaled from the controllers specified in this BGP multicast controller draft. It could also be signaled hop by hop from leaf to roots, specified in different draft. So the essence of BGP signaling from controllers for multicast, if you look at this picture on the right side, a BGP update message includes the NROI, and route target, and tunnel encapsulation attributes. The NLRI part will encode two things. One is that the tree identification. For different kind of trees, we will have a different NLRI route type. For example, for IP multicast, we'll encode the source address and group address. For SRP2MP, we encode the candidate path, the root ID and tree ID. And for MLDB tunnel, we will encode MLDB flag in the NRRI. The NRRI will also encode the targeted router. If you look at the picture on the right side, we have the controller at the lower left bottom of that picture. And in here, we have 5 routers here. The route reflector happens to be in the forwarding path itself. So if the tree is routed at R1, and with RR being the replication points, and R2, R3, R4 are the leads, here the controller will originate 5 BGP routes. Each route is targeted at a particular router, R1, R2, R3, R4, and route reflector itself. So that's that particular router and particular route is used to set up a forwarding state on that targeted router. So NRI will encode that information. And then a route target is attached to that BGP update so that the route for R1 will only be propagated to R1 and imported by R1. The route for R3 similarly will only be propagated to the R3 and imported by R3. And finally, we have this tunnel encapsulation attribute that encodes the forwarding information. So let's take a look at the tunnel encapsulation attributes. Tunnel encapsulation attributes was initially designed for unicast purpose. It encodes a list of tunnels, which could be of different types. In unicast case, when a tunnel encapsulation attribute is attached to a unicast route, then the matching traffic will be ECMP'd or load balanced out of one of the listed tunnels. Now, if it's used for BGP multicast, then instead of ECMP or load balancing, then the matching traffic will be replicated out of all the listed tunnels in that tunnel encapsulation attribute. Here, the tunnel is quote-unquote tunnel, meaning that it's just a way to represent a replication branch, which could be that to a directly connected router, downstream router. In that case, no actual tunnel is needed, or it could be to a downstream node that is not directly connected. In that case, a real tunnel is needed. So here, a tunnel can be of a type or a new type called any encap, which means that we don't care how we get to the downstream node. It could be native forwarding if it's directly connected, or it could be MPLS tunneling or GRE tunnel or SR or P2P pass, whatever. It's just any way of getting to a downstream node is fine. A tunnel could carry some, in the tunnel encapsulation attribute could carry sub TLVs. One example is RPF sub TLV. This is basically indicating that this tunnel is used for receiving traffic from upstream. It's not for replicating traffic. If you are familiar with the PIM protocol, you remember that SG multicast forwarding state includes an incoming interface and a bunch of outgoing interfaces. Here it is similar. The RPF tunnel is the incoming interface in the PIM, and other tunnels are like outgoing interfaces in PIM. Each tunnel could include a tree label sub TLV to identify the incoming or outgoing tree label. It could also include other information for more complicated scenarios. If you look at the example on the right side, tunnel 1 is used to identify the upstream information which means that if you receive a incoming packet with a tree label 100, then the router will know that the traffic needs to be forwarded out of three branches. One is the first branch is identified as tunnel 2 to 10.2.1.1 with outgoing label 100, so on and so forth. And in this case, for the third branch identified by tunnel number 4, we will use a different tree label 200 to a downstream node with address 10.4.1.1. SR-MPOS versus SRv6. I want to point out that SR-P2MP or even MLGP P2MP, when signaled by BGP, they can work with both MPOS or SRv6 forwarding plane. And we only need a very minimum extensions in the tunnel encapsulation attributes to use it for SRv6 forwarding plane. I'm going to skip the details between the here about the different forwarding planes, but the slides are there. So why am I only talk about the BGP-MCAST signaling in this presentation? The reason is that I believe that it is the bestest option here, better than PSAP for two reasons. One is that with PSAP, you need one PSAP session from the controller to every tree node, as shown in that lower right picture part of the picture. In the unicast case, you need one PSAP session to every edge node, but you don't need PSAP session to transit nodes. But if you use PSAP to signal SRP2MP, then you need PSAPtions to the internal routers as well. However, with BGP, you only need one BGP session to one of the BGP speakers in the network. You can add another session for redundancy purpose, but that's all you need. In this picture, we have the one BGP session to the route reflector in the middle, and then the controller sends all the BGP routes towards that one BGP speaker, and then the BGP infrastructure will finish the rest, will get the routes to the public routers. And the other reason is that BGP multicast signaling provides great coverage and extensibilities. With the same procedure, we can use for both underlay tunnels and overlay multicast, whether it's IP multicast or SRP2MP or MLBP or any future types of multicast tree. We can even use this to replace the BGP and APN, and which will work well, very well in certain scenarios. In this presentation, we're not going to talk about BGP and APN replacement, but it is actually covered in the IETF draft I mentioned earlier. So it can also support bidirectional trees. It can be used for both hop-by-hop or controller-driven signaling. It's easily can be easily used for end-to-end inter-region support and integration with Classful Transport, which we'll be talking about next. So inter-region multicast. Basically, an end-to-end multicast tree or tunnel can span multiple regions. Here, a region is an AS or an ISP area. We can use different signaling in different regions, and the border routers, regional border routers, will be responsible for stitching them together. For signaling across a region, we can use Inband signaling, or we can use overlay signaling over a region. So in the overlay signaling case, the internal routers do not keep state for end-to-end trees. But with Inband signaling across a region, the internal routers will maintain the states for each end-to-end tree. Here are some examples. We have metro region 1 and 2 on the sides, and we have a core region. And let's say the routes are on the left side and leaves are on the right side. It could be that we have end-to-end IP multicast tree for a source group. And in the region 2, on the right side, we can use PIM signaling. And when it comes to core region, we can do MLDP inband signaling. And then on the region 1, we can use BGP signaling. Similarly, if we have SRP P2P tunnel spanning those regions, then we can use PSAP for region 2, BGP-MCAST signaling for SRP 2P in the core region, but it's controller driven. And then in the metro region 1 with BGP SRT signaling, which I didn't talk about. The key idea is that different technologies can be used in different regions. One thing I want to point out that in case of hop-by-hop signaling, inside the region, the routers need to determine the reverse path forwarding neighbor, and that does require the routes towards the routes. And in some deployment scenarios, for example, BGP LU, the internal routers actually don't have the route to the routes, the tunnel routes. In that case, the RPF performed by the internal routers need to be towards the upstream border router instead of the route itself. And that upstream border router information can be encoded in the various protocols, whether it's a PIM or MLDP or BGP multicast. And then overlay signaling, obviously it's over a region. The internal routers do not keep state for end-to-end trees anymore. In this example, RBR2 will signal to RBR1 directly. This could be done by BGP and VPN. It could be done via MLDP over targeted sessions, and it can be done by BGP-MCAST. I want to point out for MLDP over targeted session or BGP-MCAST, there is actually no difference between overlay and inband signaling. It's just whether the upstream or downstream nodes are directly connected or not. So after the RBR to RBR signaling, then the upstream RBR, which means regional border router, will tunnel traffic to the downstream RBRs. That could be either ring server replication or P2P tunnels. Okay, we can talk about multicast with classful transport very quickly. BGP Classful Transport is some IETF work that is led by Juniper. It basically the underlay routes are classified into transport classes. They are advertised by a new CEFI called the Classful Transport CEFI, and they have attached a route transport class route target attached. Those transport route targets specify the transport class, and also it is used to control the route propagation and importation. And then the service routes will carry a mapping community. That mapping community will map to the transport class, which means that it specifies which underlay routes to be used for to resolve the protocol mix-up. So when it comes to multicast, multicast tunnel or multicast tree could be an underlay tunnel for a particular transport class, or it could be an overlay multicast tree that needs to use a particular underlay tunnel with a particular transport class. So either way, the BGP multicast signaling can carry a mapping community to map to the transport class, and that will affect the path or tunnel selection between upstream and downstream nodes. It could also be used to affect upstream node selection for a downstream node. So those are very high level information there. Um, if you have want to know about more details, we can have deep dive sessions arranged. So, summary, we can have various options for multicasting segment routing networks, whether they stick principal or SR principles or not. It's really up to the operator's choice. Um, if we're not using beer and we're not using traditional multicast technology, then BGP multicast to me is the best option. It only use a single session from the controller to one of the BGP speakers. It provides great coverage and extensibility. And if you use BGP multicast to signal MLDP, then there are additional benefits that simplifies the transition from existing MLDP deployments and the flexibility and extensibility due to the opaque structure of the MLDP FAC. And we talk about end-to-end inter-region multicast, where different signaling methods can be used in different regions. And also, BGP multicast signaling can easily integrate with BGP Classful Transport. So that's the end of my presentation here. We have a few minutes for questions or comments.